It's Ken, the Metal Professor, here with another issue. Is issue the right word? I have no idea. Another entry into what I hope to be a pretty lengthy sequence of videos, Metal Professor's Math Coaching MPMC. This is intended for people who are taking math at the high school, upper high school, college level, say pre-calc, calc 1, calc 2, calc 3. I'm trying to pace these out so that topics I talk about during the semester kind of line up with what people in some of those classes might be experiencing at the time. Right now, it's just warm up because it's late August and the semester's just getting started. Nobody's deep into the weeds just yet. So this is number 2. Check out videos 0 and 1 if you are so inclined. Today, I'm just going to introduce, I guess, what I would call a survival guide. Some brief foods for thought to help you focus on your problem solving. Mostly in the calculus realm. Now, whether it's 1, 2, or 3, it doesn't really matter because those topics all swirl around some of the same things that I will dabble into here. This is not an exhaustive overview of any one particular topic, but just dipping our toes in the water in a few different places as reminders of things that you should keep in mind, especially when you're starting to get stumped, right? So when you're taking an upper level math class, you're going to start encountering functions that start looking familiar. The same sets of functions over and over, but different varieties within those types. And so you're going to need an intuitive sense of how these functions behave. And you're going to spend a lot of energy in calculus or even pre-calc figuring out where something is equal to 0. Now, if you've already taken Calc 1, you know this and you know why. If you haven't, you'll get there, but finding out where things become equal to 0 is a really big deal in a lot of cases. And so I'm going to point out some highlights or markers on some graphs of functions that can help you with that. I'm also going to recommend that when you are solving equations and you come up with values, get used to just leaving those numbers in exact form. Don't go overboard trying to get decimal approximations because what you're doing is basically spoiling a perfectly good number. But I'm going to sweep through several types of functions here, brief discussions about the anchor points that you might want to become familiar with on these functions to use as is necessary. So when you're taking classes like these, you're going to see the exponential function a lot, like 4e to the 3x. You're going to see logarithms. Now, there's different bases. There's log base 10, log base 2, log base almost everything. But the natural log, the one that kind of goes hand in hand with the e exponential function, that's sort of the big deal. You're going to see trig functions, 7 sine of 4x or -8 cosine of x over 2. These are the varieties of functions you're going to see. You're also going to see polynomials. You're going to see rational functions. You're going to see the other 4 trig functions, which are defined based on sine and cosine. If you're lucky, you're going to get to encounter hyperbolic functions, which are actually exponential functions at heart, even though they are named after the trig functions. There is a story to that. You will also encounter piecewise functions, which isn't necessarily any one of these particular types. It's just the idea that very often functions have just one recipe, but other times, for whatever reason, you might say, here's a function. I'm going to give input to the function to get output. And the recipe I'm going to use to calculate the output might be different for x values from 0 to 4 as it is from x values from 4 to 10. And that's what turns into a piecewise function. So sweeping through some of these very quickly just to point out some highlights to start you thinking along these lines. Haha. Here are 2 versions of the garden variety exponential function y equals e to the x. The black curve is y equals e to the x. The blue curve is y equals e to the negative x. You should understand the trends, why these graphs look the way they do. For y equals e to the x, as we plug in x values that get bigger and bigger, the output would get bigger and bigger. for y equals e to the negative x, as we plug in values of x that get more and more positive and large, the value of the function should be getting smaller and smaller, because remember, e to the negative x is 1 over e to the x. So if e to the x is getting bigger, e to the negative x is getting smaller. A very interesting thing you should notice / remember about this pair of functions or any other varieties like them, they're never zero. These graphs never cross the x-axis, at least in their purest form like this. Now you can add additive constants to move them up or subtract constants to move them down, and sure, there you're going to start encountering zeros. But just y equals e to the x itself, y equals e to the negative x, there are no roots, there are no locations where these functions have a value of 0, and that's good to know. However, even though the function itself might not become 0, expressions built on these functions could very well be 0. E to the 2x itself is never 0, but 4 e to the 2x minus 5 may very well be equal to 0. And in Calc 1, for example, there are lots of cases where you're going to have a function in your hand and you're going to say, to answer this question, I need to learn where this function is equal to 0. So suppose it's this case, just as a reminder of how this works. We solve equations like this using the onion principle. We are trying to dig into the location of the variable and we're peeling away from the outside in, like an onion. It's also like an onion because it stinks. However, for this equation, we're going to add 5 to both sides. We're going to divide by 4. So up to now, we're at e to the 2x equals 5/4. Now, in order to dig into the x, we have to get rid of the e. Do not divide by e. That isn't how this works. This is like math prison. This x is trapped up here in the exponent. In order to dig into the x, we have to get rid of the function e first. Now, how do we get rid of entire functions? We apply their inverses. If you don't remember what that is, that's a whole other topic. Not going to say anything more about it here, other than to remind you that the inverse of e to the x is the natural log of x. Inverses wipe each other out, much like the square root and the square, right? If you're solving something squared, you're going to take the square root because that eliminates the square, right? That's how inverse functions work. So if you watch the other video that I did, one of the other ones, one of the things I tried to stress is to remember who is in charge of this stuff when you're working on it. E to the 2x equals 5/4. Who is in charge of this expression? We are. We know that we would like to apply a natural log to this left-hand side in order to eliminate the e and extract the 2x by itself. So dang it, we're going to apply the natural log to the left-hand side. We just have to do it properly by making sure to do the same operation to both sides. So we take the natural log of both sides of this equation. The natural log and the e do to each other what they do. In other words, they're out of there. Now we're left with 2x equals natural log of 5/4, and then solve for x by dividing by 2. Okay, so x equals 1/2 natural log of 5/4. Gross. Okay, well, let's see what that number really is, right? So I'm taking out my calculator, and I'm going to start punching buttons to try to see, no, don't, right? This number is happy the way it is. Don't number shame it. It's 1/2 natural log of 5/4. If you waste time grabbing your calculator, punching in all these characters and getting a decimal approximation, you are going to present a worse representation of this number. It will be an approximation of this number. The exact version of this number is 1/2 times the natural log of 5/4. Anything else is less, right? The square root of 7 is the square root of 7. You don't need to go off on the side and say that it's 2 point something, something, something. Okay? So keep exact values when at all possible. Now, sometimes exact values just get nuts. In that case, okay, if you're trying to get an intuitive sense of what a number is, fine. Go look at a decimal approximation. But when you're solving problems, keep this like this until there's a reason not to. Now, we brought in the natural logarithm, so here are some samples of that type of function. The black curve here is the garden variety y equals natural log of x. An anchor point, a very important point to notice, is where it crosses the x-axis. That is the root of this function. It's where the value of the function is 0. And notice that this function hits y equals 0 exactly at x equals 1. Okay, and if you remember the definition of the natural log function, well, fine, then you know why that happens. But even if you don't, if you know that the function natural log of x has a value of 0 when the input is 1, that is good stuff, even if you don't really understand what the natural log function is to begin with. The blue curve is the natural log of 3x minus 2. It also happens to cross the axis at the same point. So you might think, every natural log function is going to go through that point at 0, 1. Well, not so fast, because the green curve is the natural log of 3x plus 2, and that's been shifted. Okay, now they all have the same shape. They're kind of swooping from lower left to upper right, but some of them cross the axis at this point, some of them cross the axis at other points. But knowing the anchor point on the fundamental natural log curve is the key to figuring out the crossing points for any other version of the curve. Okay, in equation form, we're going to query this function and say, hey, function, where do you cross the x-axis? Where do you have a value of 0? So we set this up. Now, there's a couple of ways to solve this, one of which is remembering that special anchor point. That special anchor point tells us that the natural log of anything is going to be 0 when that thing is equal to 1. The natural log of x is 0 when x is 1. Or the natural log of 3x minus 2 is 0 when 3x minus 2 is equal to 1. Solve that for x and we get x equals 1. And that's why this blue curve also crosses the axis at x equals 1. Now, the other way to solve this is, if we pose our query again, is to use the language of inverse functions. But remember, e and natural log go hand in hand. So if we want to eliminate the natural log, we apply the exponential function, raise both sides into the exponent of this. Remember, we can do anything we want to this expression because we are in charge. Whatever we want to do to it, we can do to it as long as we do it properly. We want to lift the left side and so also the right side up as exponents of e. The reason we do that is then e and natural log, they're out of here. And now we're back to x equals 1 as that solution value. Now let's go back to this curve. Look at the green curve. This green curve happens to cross the x-axis at exactly -1/3. Right? There's -1/2 right there at the boundary. That right there is -1/3. Why? Right? Well, that's because this green curve will hit 0 when 3x plus 2 is 1. Solve 3x plus 2 for 1, you end up getting x equals -1/3. If that doesn't make sense, pause this and go fiddle with it. Now, here is a different kind of function, a rational function. This is looking pretty gross. Rational functions have anchor points to keep an eye out for. It's not the same anchor point like it would be, that the natural log function crosses the x-axis whenever its interior is equal to 1, right? That's a very specific thing. However, there are still rules about rational functions. Remember, rational functions are functions that are ratios of two polynomials. Polynomial on top, polynomial on the bottom. Generally, we will call the numerator p of x and the denominator q of x. Those are both polynomials. The whole function will hit 0 when the numerator function hits 0. The whole function will be undefined when the denominator function is 0, right? Because you can't divide by 0. This presumes it's been simplified and things you can cancel have already been canceled. So where is the solution to this equation? Here's a function. We're giving it a query. Hey, function, where are you equal to 0? Well, equal to 0 when the numerator is 0. It just so happens that numerator can be factored pretty easily. Remember, I made these slides. I can make up easily factored functions if I want to. And so this shows us that the numerator, and so also the entire function, will be 0 when x is 0, 2, and 3. All right. Again, this is under the umbrella of, in Calculus 1 in particular, you're going to spend a lot of energy discovering where functions are equal to 0 This is a messy looking function, but the search for where it's equal to 0 isn't all that bad as long as you know what to look for. Okay. Also in Calc 1, if you haven't gotten to it yet, you're going to get some pretty cool tools that will help you draw a nifty graph of this monstrosity of a function without breaking too much of a sweat. But it all starts here, right? It all starts finding the roots at 0, 2, and 3. And here's a graph of that function. So you can see the root there at 0, here at 2, and then here between 2 and 4 right there at 3. Okay, this picture of the function, and if we zoomed out, a bigger picture of the function would never have any asymptotes or discontinuities because this function never goes to 0 in the denominator. So this function is defined for every value of x. All right, and everybody's love of their lives in math, trig functions. There are 6 trig functions. However, if you know the good stuff about 2 of them, then you automatically know the good stuff about all 6. So focus on learning the properties of sine and cosine because that information can be brought to the other 4. This story we're talking about right now is solving equations where you're taking a function and setting it equal to 0. For the sine function hits 0 when whatever is inside the sine is a multiple of pi. The sine of 0 is 0. The sine of pi is 0. The sine of 2 pi is 0. The sine of negative 6 pi is 0, right? And if the interior is more complicated, well, whenever that interior is a multiple of pi, you're going to get a root, okay? So if we're trying to solve sine of 2x minus 5 equals 0, well, that is going to happen when 2x minus 5 happens to be a multiple of pi. 2 pi, 3 pi, 4 pi, negative 2 pi, negative 3 pi, negative 4 pi, 0 pi, etc. So solve this for x, add 5 to both sides, divide by 2, and here you go. So there are lots and lots of values of x where the sine of 2x minus 5 hits 0. Now this graph is a mess. The black curve is just the garden variety sine of x. It hits 0. It has a root when x is 0, when x is pi, 3.14-ish, when x is 2 pi. Now, the sine of 2x minus 5 has these other locations of roots, but you can see where they are because that red curve is the sine of 2x minus 5. So the roots have shifted a little bit, but there's still lots of them, and they're still relatively easy to locate. Now, carrying on that idea, if we switched over to cosine, would you remember information about the graph of the cosine function? Just the fundamental cosine of x graph. It also oscillates. Where does it cross the axis, the x-axis? Not at pi, 2 pi, 3 pi, but where? And can you then use that information to say, well, if I have the cosine of something that's a little more complicated, and I need to know when that function's going to hit 0, what do I need to learn about what's on the inside? Where does that have to land to make the whole function equal to 0? See if you can go dig that out for yourself. Also, in terms of taking information about sine and cosine and extending it to the other 4 trig functions, tangent of x is sine of x over cosine of x. So where would we find zeros of tangent of x? Where would we find places where the tangent function itself has a value of 0? Where would we find locations where the tangent is undefined, right? All of that information is based on what you know about sine and cosine. So don't panic because there are 6 trig functions. If you know a lot of good stuff about 2 of them, then by default, you know a lot of good information about all the other 4. That story in itself takes weeks in a pre-calculus class, right? And there's still 3 other trig functions to go through besides tangent. So we're not going to get into it. I'm just kind of telling you what to think about. As you're getting geared up for calculus 1, 2, or 3, I just wanted to give you sort of a quick overview of the idea that you got to get good at setting a function equal to 0 and solving it. You're going to have multiple different types of functions you have to handle. But if you have just a core amount of knowledge about the fundamental versions of those functions and the behavior of those graphs, you can use that function, that information, to extrapolate to information about all the more complicated varieties of those functions. You don't have to start from scratch every time the function changes. Okay, so this was like the second sort of introductory, getting warmed up for a semester of math videos that I've posted. Pretty soon I'm going to start narrowing down to very, very specific types of content. Again, I'm going to try to pace these to match where you might be during the semester if you're in Calc 1, 2, or 3 at any one time. I won't be able to nail it precisely, but I should be pretty close. If you are coming up on topics you think you might like some information about in advance or as review, drop me a note to metalprofessor@gmail.com and I will try to work it into some of these videos.